Yeah, hi. I would like to tell you something about the arithmetic loophole in Bell's theorem. The main result was published in January in Arithmetic Copernican. It's on the archive too, if you want to find it. Here you can see the sequel, a recent one, which appeared on Friday. And in short, I claim that it is possible to formulate a local hidden variable theory where formulas of this type are possible. These are Clauser-Horne formulas, which are basically regarded as impossible on the basis of standard proofs based on Bell inequality. Well, I claim that it is possible to do it. Of course, the trick is in the exact meaning of this multiplication and exact meaning of this integration here. Yeah? But because of this type of formula, the known proof of security of 2-qubit protocols in quantum cryptography fail, in my opinion. So we have no longer a proof that quantum cryptography is fundamentally secure. So in this sense, quantum cryptography is in a situation similar to the classical RSA-based cryptography, where we're regarded as fundamentally insecure because we are not able to prove that an efficient factoring algorithm does not exist, not because we know such an algorithm, yes, but because we don't have a proof. The proof doesn't work, or we don't know how to prove it. Here, I claim that standard proofs of Eckert-type protocols, or Bennett-Brassard-Mermin-type protocols, or Bennett-Brassard 84 protocols will not work, simply. Now, there are certain technical aspects which I will concentrate on. First of all, the meaning of this product, which is from the so-called projective arithmetic. Hidden variables in my concrete model will be just real numbers, although the meaning of real numbers, well, okay, demands some discussion. These characteristic functions which you see here are just basically ordinary characteristic functions, although they are projective bits valued. I will explain later what I mean by this. And finally, the integral is non-Newtonian. Non-Newtonian integral was introduced for the first time by Grossman and Cass in 1972. Then it was rediscovered by Papp in 1993, and it's used basically in many branches of applied mathematics, we can say. Now, physical aspects. So first of all, I claim that arithmetic is as physical as geometry. We are used to such a phrase that geometry is physical, but typically we mean by this geometry from general theory of relativity, where interactions like gravity are modeled by geometric structures. Well, what I would like to stress is that in special relativity, we first of all have a physical arithmetic of velocities. Yeah? I will come to it. And this arithmetic is exactly projective in the sense which I will use here in my construction. Moreover, there are problems such as dark energy or dark matter where there are arguments that this could be some sort of arithmetic problem in the same sense. I will not discuss it here in this talk, but just point out that such a possibility exists. So if really projective arithmetics are as physical as those from special relativity or perhaps dark energy problems, what about if they are physical at the hidden variable world? This is the question. Yeah, okay, so we will begin with this projective arithmetic. I will just discuss it on the example of velocities, but it's clear that it's not restricted to velocities. So the example shows that nature is using arithmetic in a slightly different way that, well, Galileo would think of arithmetic, or Diophantus, for example. We know, everybody knows this, but I just want to create, with this example, a context for our discussion. So we have velocities. We have a collection of platforms, and I assume that the relative velocity between two neighboring platforms is just 1 meter per second. So it means that it's non-relativistic velocity. And we can walk from one platform to another. So in order to move from platform to nth platform, we just walk on this platform with velocity 1 meter per second and then jump to another one. We can do it an arbitrary number of times, of course, and the relation between two neighboring velocities is just standard, the Galilean, we can say, because this delta v is 1 meter per second is highly non-relativistic. Therefore, we don't have to, apparently, we don't have to worry about the exact meaning of this addition. But, well, what happens is that we can do it an arbitrary number of times. We can walk from one platform to another and so on. Yeah? And after a huge number of steps, like 10 to 10th number of steps, we will achieve huge velocity, of course, where this approximation will not be valid anymore, right? So that's one aspect, of course. So at certain, this formula here is exact because we can really add these velocities for any delta v. This approximation, standard approximation, is of course valid only for just jump from one platform to another. And by the way, it shows that there is something wrong with the induction principle. Yeah, here, if we just accept that we can jump from one platform to another according to the non-relativistic way, then we are in trouble with the induction principle, basically. Yeah. That's one element, but I will not concentrate on it. Now, there are two other implications of this problem. Namely, if I do it, if I'm moving from one platform to another and I do it k times, it should be somehow equivalent to multiplication, to performing a single step by k times delta v. Yeah? If we have addition, we automatically have some sort of multiplication, at least of real numbers, of natural numbers. Okay? So we would have to understand what this multiplication means, and moreover, this k times is subtle. It means that it's not obvious at this stage what should be meant by k times, because we don't know yet exactly what's multiplication. So this k, in fact, this number which we multiply could be a function of k. So we have to clarify these 2 points. And just a brief historical remark that the problem we encounter here is essentially a sophistic paradox known from 400 years before Christ. Yeah, it was formulated by one of those Greek sophistic philosophers, essentially. Yeah, so now there is a lot of literature on this heap paradox, fuzzy sets, and so on. Are developed in this context. From our perspective, the solution of this paradox is known because we have this exact relativistic formula for addition. So there is no paradox at all. Simply, when we do this step here, we already should not use ordinary addition, but we have to use the exact addition. That's basically the solution of the paradox. So we have to work with the exact generalized addition, even though we are working in such a regime of the parameters that it might seem that we don't have to worry about it. But okay, let's go to this exact calculation from special relativity. So we know that velocity is simply c times hyperbolic tangent of certain parameter, velocity parameter. And addition of velocity is simply addition of these parameters. So we have two velocities, they have two parameters, and that's how it works. If we know how to add, we can consider this kind of addition where we add the same velocity k times, and then we arrive, first of all, we arrive at the multiplication, which is implicit in this formula. I will just write it in the next slide explicitly. And then we also arrive at the exact form of this k prime, because k prime is hyperbolic tangent of k, where k is a natural number, and this k prime plays a role of a natural number, actually, in this arithmetic. This arithmetic is exactly the so-called projective arithmetic. So you have here an example of a physical system which satisfies a physical quantity, here velocity, which satisfies certain generalized arithmetic. Interesting thing is that in such a in such arithmetic or such a context, you have three fundamental velocities, not one. Typically, we say that in special relativity we have one special velocity, which is velocity of light. No, we have two more. One velocity is zero velocity, which is just a neutral element of addition in this arithmetic. V plus 0 equals V, always, in this exact sense. And we have another velocity, which is just 1, which is a unit element of multiplication in this arithmetic. And you can compute the hyperbolic tangent of 1, which is roughly 0.76. So it's, in terms of velocity, we have another fundamental velocity, which is 0.76 of velocity of light. Yeah, so there are three velocities. This, I don't think it has an interpretation in special relativity, but moreover, in special relativity, the way we are taught special relativity is that we are taught how to add velocities and how to subtract velocities, but we are not taught how to multiply and divide. Yeah? Even though adding something several times is equivalent to some sort of multiplication. And so there is some implicit arithmetic in special relativity which is not used, but is there. Yeah? And it can be made more formal, so to say. So we have certain set x, which corresponds roughly to this interval between minus velocity of light or plus velocity of light, or minus 1, 1, depending how we parameterize it. This map f is, if you look at this formula, this is this hyperbolic tangent to minus 1. So this is the inverse function. It maps this segment, minus 1, open segment, minus 1, 1, into just real numbers. So this is our function f in this notation. And this is what we do, actually. So this is relativistic addition of velocities, this is subtraction, and these are two additional operations which are not used typically, but they are there, right? They're implicit in this construction. Once we have it, we have two neutral elements of this arithmetic, 0 and 1. 0 is a neutral element of addition, which means that x plus 0 equals x. And 1 is neutral element of multiplication, x times 1 equals x. You can also, repeating this operation several times, you arrive at a natural number from the point of view of this arithmetic. Well, since you have multiplication, you have division. If you have division, you can divide by natural numbers, and therefore you have rational numbers. If you have rational numbers, you have real numbers, essentially. So this formula, this one, could be used for any real number n. N doesn't have to be even, I mean, not without this middle part, but such a definition, such a number, define f2 minus 1 of n. f2 minus 1 is just hyperbolic tangent here in this context. So this is the formula which is exactly of this shape. So 1 is hyperbolic tangent of 1, which is 0.76 in this special relativistic context. But here I would like to treat it as a kind of paradigm. But what's important for our point of view is that we have a natural definition of bits in such a context. Yeah? They are called projective bits here because this arithmetic is called projective by some mathematicians like Mark Burgin, for example. So and these projective bits will be important for my construction of hidden variable model of singlet state correlations, where, by the way, let me stress it already now, my projective 0 and projective 1 will be just ordinary 0 and ordinary 1. So I am not manipulating at this stage. What I want to simply stress that if velocities, if nature adds velocities in a different way and multiplies them also in such a way, then there is absolutely no reason to believe that velocities are exceptional physical quantities. How do we know that positions are not added in such a way, or time is not added in such a way? Yeah? The problem with dark energy are related to the problem of time, actually, the arithmetic of time, but I will not go into it. Yeah, so that's the motivation for the arithmetic. And now, since we have projective arithmetic and projective bits, we will discuss it again in a moment. What I would like to stress is that, first of all, projective bits in our model, in this model which I will use, are as real numbers as just eigenvectors of projectors. Projectors have eigenvalues 0 and 1. Yeah? So these are real numbers, of course. Here, projective bits are as real as these numbers. Then we'll see in a moment that projective bits can be as incompatible as eigenvalues of non-commuting projectors. So if you have two projectors that don't commute, their eigenvalues are 0 and 1. So these are apparently the same numbers, and yet we know that they are incompatible in a certain sense, that in the sense that sum of these two bits is not just a sum of it does not correspond to the sum of projectors, in a sense. We know it. I will not go into it. So anyway, these projective bits which I use can be as incompatible as eigenvalues of non-commuting projectors. But what's important, projective bits possess EPR types elements of reality, which is something completely different from quantum bits. Yeah? And we can correlate them, like in entangled states. That's what we want to discuss now. So first, let me return to the problem of representation of real numbers from this point of view. So a real number, like this velocity example, which is between velocity of minus velocity of light and plus velocity of light. So this is some set, and there exists a bijection of this set into real numbers. It means that this set must have the same number of elements as real numbers, which means that this is any set whose cardinality equals that of the continuum. Here I give you two examples of such sets, which are kind of pathological in some sense, because I want to stress this pathology from our later point of view. So here you have certain fractal pattern in a plane. These are counter sets, essentially, left closed, one-sided closed, so counter sets. So this is a fractal, but one can easily construct these bijection into just ordinary real line. It's even shown how it's done. I will not discuss it. Here it's a half plane, left open, so 0 is not there. And here the bijection is just given by the logarithm, essentially. Now, I claim that these two strange sets have all the properties of real numbers. And this is guaranteed by the projective arithmetic, which is implicit there. The projective arithmetic is defined by our bijection. It means that if I want to add, for example, this number to this number, I first move them by our function f into this line. Then I have these two numbers, so I move them here. Then I add, subtract, multiply, divide, whatever I want. So I obtain a number here, and then I move it back here. The same happens here. So if I want to, for example, subtract, I want to perform an operation like 1 minus 5. So it should be, naively it's a negative number, but it's not a negative number here. It is in a sense, yes, but not in the naive sense, because if I want to move, for example, from subtract from 1, I want to subtract 5, then I first move 1 here, then move 5 here, then I perform subtraction, I obtain a certain real number, and then I move it back. So negative numbers here are those which are contained between 0 and 1, for example, in this arithmetic. If you have a problem with this kind of representation of real numbers, just think of it as a kind of activity pattern of our brain. Yeah? If you think 5, then you have certain activity pattern in your brain. If you think 5 plus 3 equals 8, then at each stage of this your brain performs certain activities, and it has certain neural activity, and it could be a fractal configuration generally. So I want to have something pathological for certain reasons, which I will immediately explain why. Okay, first, because of this isomorphism, because of this bijection, all the arithmetic operation in these sets x and y here are just inherited from the real line. So just commutative, associative, and multiplication is distributive with respect to addition. Yeah, that's how it's called probably. So we have two arithmetics in these two sets. Because we have two arithmetics, we have two types of bits, of course. Yeah? So this is a neutral element of addition, this is neutral element of multiplication here, and they are given by this form. It just works, you know, x plus 0 equals x, x times 1 equals x. The same happens here, of course. Yeah, you don't have a problem with such formulas, but you can add 1 plus 1 equals 2, that's okay, no problem with this. The same happens in the other set, but what should we mean by 1x plus 1y? It makes no sense, because 1x is for example this point, 1y is this point, is this one. Yeah? So this one belongs to the fractal subset of R2. This is a point from R1. So naive addition of them is impossible. You can invent some sort of addition, but not the naive one. So naive addition doesn't work, even though you have real numbers here in the background. Here we have three arithmetics. We have arithmetics in X, arithmetics in R, so to say, the ordinary arithmetic, and other arithmetic in Y. Yeah? So all those mixed additions are just as impossible as addition of eigenvalues of two non-commuting operators. Well, you can't add a point from the plane to a point in a line, basically, and not in a naive way. Yeah? So they are incompatible, yet they can be correlated, of course. And they are correlated. Why? They can be correlated because they are equipped with common elements of reality, as I call them, arithmetic elements of reality. So 1x is the image of ordinary 1, of the same one as this one. So 1y and 1x have some common element of reality, and yet you are not allowed to add them. Yeah? So that's why these projective bits are somehow analogous to quantum bits, and yet they are equipped with some sort of elements of reality, and these elements of reality can be used to perform random experiments. Yeah? And you have red point is clearly correlated with red point, and blue point is correlated with blue. They can appear randomly. And this line, which joins these ones, is an element of reality here, frankly. Yeah? So correlation of incompatible bits is possible here, like in entangled states. Correlation is by means of the common element of reality, and so we can have something like a classical analog of EPR correlation. So the question is if we can use this kind of structure to mimic quantum probabilities or quantum cryptography or fake it. Yeah? So this is the first aspect of our construction, so to say. Now we come to the second aspect. So we have projective arithmetics, and now I claim that we can the whole hierarchy of such arithmetics. In particular, we have a hierarchy which I call Copernican, because we would like to understand if our arithmetic, our human or macroscopic arithmetic, is somehow privileged in this world. Yeah? I claim that it's not privileged, but I'll just explain what do I mean by that. So we have, let's say now, my set X, which corresponds to this weird, so to say, representation of real numbers, it's just again R. So we have this function, this bijection, is from R into R. I want to map it the same R into R because I want to consider compositions of such bijections. So a composition of bijections is again a bijection, so it can be used for our construction. Well, so G denotes F2 minus 1. G to K is just a composition. G to minus K is just a composition of inverse G's, which means composition of F's. G to 1 is G. G to 0 is just identity map. That's my notation. Now, because G to K is a bijection of reals into reals, then I can introduce my projective arithmetic, which is defined by this. I assume that all these G's are strictly increasing functions in order to not to modify the ordering relation. Less or equal is the same for all K's. So as you can see here, we have certain set R, and we can equip it with infinitely many arithmetics. Yeah? And typically, if you look at this, because K G to 0 is the identity map, then R0 is just a sort of ordinary arithmetic, but I will just question this formula in a moment. But here we have a countable family of arithmetics. And arithmetic, in this understanding, is like an algebra. So it's a set equipped with 4 operations: addition, subtraction, multiplication, and division, and ordinary relation. But ordinary relation is the same for all these arithmetics. I don't want to manipulate with ordinary. Okay, so we have such a definition, but then since K is arbitrary, we can ask what's the relation between... first I have to act, if I act on both sides of these formulas with G2 minus K, then this G2K disappears, it appears here at the left-hand side, and I obtain this form, which shows that my bijection is simultaneously an isomorphism of arithmetics, which means that it maps plus in the kth sense into ordinary plus, or plus 0 if you want, and you have this isomorphism. So it maps RK into R0. That's how it. So that's important. Now, because we know the explicit definition of operations at RK, we can ask what's the relation between these RK and RL, for example. Here's the formula. And if you look at this formula, it's basically similar to those we had for L equals 0. Moreover, the same isomorphism, G2 minus K, which we had here, which is isomorphism or RK and R0. Now the same function looks like an isomorphism RK plus L and RL. So that's how it looks like. Now the same function. So how do we know that what we call ordinary arithmetic or human or macroscopic arithmetic, whatever, is R0 and not RL? I claim that this is a question of notation only. We could use this formula and, well, we could work with it. Complete no problem. There's absolutely no criterion telling us which, if I write such an arithmetic with ordinary plus, so to say, whatever it means, which plus it is in this hierarchy. I claim that we have no criterion. And therefore, I introduce Arithmetic Copernican principle, which will be important, basically, that our standard macroscopic, human, whatever, arithmetic can correspond to any RL. Therefore, these weird arithmetic operations actually could be our arithmetic operations. So perhaps we are weird, but we think we are normal. That's how it works. Okay, now since we have arithmetic, now we need calculus, because finally we will need Bell-type formulas which involve integrals. And if we want to have integrals, we have to have calculus. So we need calculus associated with projective arithmetics. We will work in this context of this hierarchy. But first of all, a historical slide. So this type of arithmetic was applied to the problem of calculus for the first time in this little book by Grossman and Katz in 1972, I think. Then it was rediscovered in 1993 by Andre Papp, the author of this monograph, and here. Well, by accident I kind of discovered this in 2014. I didn't know of these contributions, but it doesn't matter. But here, for example, in this handbook of measure theory, you have a law, it's edited by Andre Papp, and there's a chapter in volume 2 where he describes measure and integral. And measure and integral here in this sense is exactly the one we will use in our work. So before we arrive at the integral, we have to, it's simplest to start with the derivative. So derivative of a real valued functions. It could be more general, but I just concentrate on real valued functions. So we have just real analysis. But then we assume, as you can see from these diagrams, I have I have a function r into r, but then I have these bijections. So I could write such a diagram, for example. And then it defines certain function a tilde, but it shows that from this perspective, we have a function a could be regarded as a function from arithmetic rk into arithmetic rl. That's what the diagram tells us. This diagram, these three diagrams are the same diagrams because f is g2 minus 1. Yeah, so you can see the different directions of these arrows, essentially. So this function, this diagram tells you that function a from rk to rl can be defined in such a way in terms of certain intermediate function a tilde, which maps r0 into r0. So this is just an ordinary function we know from university or from high school. So then here you simply define a in terms of some given a tilde. Here you have the other way around. You simply define a tilde in terms of these two bijections and a. Yeah, that's the interpretation of the diagram. Well, if you want to, for example, compute a derivative of a function of r from rl into rk, then what you have to do, just use the standard high school definition of the derivative. So you have to subtract. So first you take a, taking an argument x plus delta, but plus in the sense of the domain, which is rk. So this is plus in this kth sense. Then you have to subtract this value from this value, but you subtract in the arithmetic of the codomain, of course, because you are already here. So you have to subtract in this sense, which is lth sense, and then you have to divide by delta in the sense of this codomain. Of course, as you can see, you have certain delta k, delta l. They are even defined here in terms of our bijections. Well, it works simply. You don't have to, what's important in this formalism, you don't have to assume anything about these functions g and f. The only assumption you make is that they are bijections. They don't have to be continuous in some metric topology of R or something like that. No, bijection is enough. The only thing you have to assume technically is that this g to l and g to k are continuous at 0. So the inverse function must be continuous, because otherwise these neutral elements would not be defined. Yeah? So in order to define 0 l and 0 k, you have to know what it means gl of 0 simply. So that's the only technical assumption. It's a digression. It's not important for us. So you have a derivative. And it's a very nice derivative because it's linear and it satisfies the Leibniz rule. Of course, linearity or additivity, better, and Leibniz rule in terms of the arithmetic of the codomain, yeah, which is arithmetic here. I stress it because derivatives are additive in this sense. It means that integrals will be additive also in this sense. Yes? Now we have integral. Integral is defined, once we know how to define a derivative, and the definition of the derivative is the most natural one can imagine, we just demand that the integral is defined in such a way that the fundamental theorem of calculus applies. With the standard assumptions about continuity, differentiability, and so on. Yeah? So we want this kind of formulas to have. And again, these are just repeated, these diagrams which I discussed. And then, if you introduce this function a tilde, then you find a very simple and very useful form of the derivative and the integral, because it can be formulated in terms of the ordinary integral, ordinary like Lebesgue, Riemann, whatever, at the level of R0. So this is something we are taught at school. So this level it's something we are taught at school. This one is something we are not taught at school, yeah, generally. So here we have an ordinary derivative, let's integral, say Lebesgue integral, and this is ordinary derivative. So this level is called Newtonian, and generally this level is called non-Newtonian in this sense. Okay, so we have, moreover, notice that we are speaking about functions between different level of my Copernican hierarchy. So I have a Copernican hierarchy of calculi here as well. Now we have to concentrate on the integral, because we don't use derivatives in proofs in Bell-type constructions. We use them in dark energy problems, but not in Bell-type constructions. So here we have to concentrate on the properties of the integral. So additivity looks like this. This is something we would need in proofs of Bell-type inequalities if you wanted to work in such a context. This is a formula which is needed for Clauser-Horne-like local realistic formulas. So it defines a integral of a product of functions in terms of these tilde functions which occur here at this level of the diagram. So once you know this, then you know how to operate on this higher level. So this is something we need for Clauser-Horne formulas. This is something we would need for base rule if you want to discuss joint probabilities and conditional probabilities, and ultimately also the reduction or state vector reduction or reduction of probability due to measurements. So we need this kind of formula. Okay. Now, once we have at least certain elements of the arithmetic and calculus it implies, we come to probability. And probability reduces essentially in this context to construction of these bijections, which will guarantee that our probability will be a reasonable probability. It has to be somehow consistent with the ordinary probability we are using in experiments, because whatever mathematical construction I will perform at the sub-quantum level, let's say, it will be tested in ordinary experiments, like quantum mechanics is tested in ordinary experiments. So this will be also tested in such a way that we just count detections in some detectors. So we count number of successes and divide by the number of trials, and this should be a result which is consistent with some theoretical formula which is produced at some theoretical level. Yeah? So then we have to simply, the fact that we are going to speak about probability imposes certain restrictions on the form of admissible bijections, but yet it will turn out that these are not completely trivial bijections. So it's not that f of x equals x. No, it's more general than that. And we have here, in order to do it, we have to consider two lemmas. One lemma, I don't know if it has a name, if it's known in the literature, I found it just by accident in a sense, is the following: that if you have binary probabilities, which means that you have two events, p1, p2, they sum to 1, and you want to find a function g such that for any p from this 0, 1 interval, this is just again a probability. So g of p must be a probability, so it must be a non-negative number and it must sum to 1 in such a way. Then it turns out, this is the lemma, that g of p has a unique form. So it's a 1/2 plus h of this argument, where h of x is antisymmetric function. Yeah? So any antisymmetric function will do. That's very important. Therefore, we have an infinite, continuous even, hierarchy of such models, because any antisymmetric function will produce, by this formula, a function which satisfies this formula for any p. So that's one important aspect. Second aspect is the following. Here we have a binary event, yeah? P and 1 minus p. In the Bell theorem case, we have 4 events, plus plus, plus minus, minus plus, minus minus. So we have to somehow deal with 4 events, and the lemma is the following. But we have certain additional properties of these Bell-type probabilities, or singlet-state probabilities, namely they are rotationally invariant. If they are rotationally invariant, it means that these partial sums are 1/2, which means that probability of plus at the site of Alice is 1/2 in any direction, and the same with Bob. Yeah? So we have these additional conditions which have an interpretation in terms of rotational symmetry, physically. And then it shows that if you have a solution of lemma 1, of G for lemma 1, then you have a simple solution for such an event. Now, such a 4-bit structure which occurs in the Bell or Clauser-Horne inequality, or Clauser-Horne-Shimony-Holt inequality. two-bit inequality in general. Okay, so now it remains to take such a function. It is defined on a certain interval. It should be extendable to the bijection of r into r, so it must be a bijection on the interval. No problem with this. And then we have to do it. So, well, that's an example. So you just first define something at the level of the interval 0, 1/2. Why? Because of the scaling function. Such a function must have a fixed point at p equal 1/4. This function has p 1/2. This function for 4 bits must have a fixed point at 1/4. So that's what you see. Yeah? It's indeed at 1/4. It's again 1/4 f of this function is g. This is the function g. So which is f to minus 1. Yeah? That's how it looks like. Here I show it from -1 to 1. Here from -10 to 10. So you can see that kind of correspondence principle, but we'll not discuss it. Both functions have infinitely many fixed points at all these quarter numbers. Now, in order to have probability, so we have certain arithmetic. Now, I started with certain function which is derived from certain probabilistic considerations. Then I extend it to the function which maps r into r. It's a bijection. Therefore, I can use it to formulate arithmetic, projective bits, and so on. By the way, projective bits will be unchanged because projective bits, if f2 is f2 minus 1 from 0, or g of 0 or g of 1, which means, and this is function g, so it has 0 at 0 and 1 at 1, so it means that bits are unchanged. Projective bits are just 0 and 1. Yeah? So we have arithmetic. If we have arithmetic, we're going to have calculus. We have certain restrictions on our g because they come from these lemmas, probabilistic lemmas, because ultimately I want to use them to construct the singlet state probabilities. Now, in order to have Clauser-Horne probabilities, I need characteristic functions. So first of all, I begin with ordinary characteristic function on a circle. So I have a circle. Alpha is certain parametrization of the circle. So alpha means that this point corresponds to angle alpha, yeah? Somehow computed. So this is a characteristic function equal 1 here and 0 here. Now this is the tilde level function, which means that this is at the level of r0 into r0 in our diagram, which we discussed. But it defines through the diagram a characteristic function at the level of R1 in the sense of arithmetic, yeah, L and K equal 1. So we start with this lower level, ordinary level, the one we know from all we have learned at school, and then because of our bijections, we in this way introduce characteristic functions at the level of our arithmetics, but they are still 0 valued and 1 valued because 0 and 1 are unchanged by our bijection, which you can see here, which I showed you, right? So these points are on the diagonal. So values are again the same. Now, so these functions at this level define a function at that level, which looks therefore as follows. And as you can see, these characteristic functions here, they are formulas for any L. Here L should be 1 because I'm just working for F to 1 and G to 1. Yeah? But anyway, it's valid for any L. As you can see, these characteristic functions behave as just ordinary orthonormal projectors. Yeah? They sum to 1 in the appropriate sense. They are orthogonal and they are projectors. If you square them, they don't change. So this defines me the structure of my functions, which will appear in my Clauser-Horne formulas, and simultaneously it shows how they look like, how the projection postulate will look like. Now, bad news for Bell's theorem. Yeah? And now if I'm using these constructions, where rho is a non-negative constant, by the way, number, and then, as you can see, you can just insert everything into our integral, compute it, and then you have exactly quantum probabilities, which means that these non-Newtonian integrals with these non-Diophantine projective arithmetics here just give quantum probabilities. Yeah? So it means, by the way, that you are not able to prove Bell inequality for such a system. Why? Why are you not going to able to use? Why is it impossible to prove a Clauser-Horne inequality for such an expression? Well, because of the additivity property of the integral. Let me go back to the formula where I had, because of this formula, essentially. Yeah. That's why I'm not able to I'm able to prove a Bell-type inequality, but it will not be the standard one. Yeah? So from this point of view, quantum probabilities will not violate this inequality, which you will be able to derive. I will not discuss it here. You can find it in my paper, because I compare different inequalities. So, as I said in my first slide, I'm able to reconstruct singlet state probabilities in such a way. Well, can I go beyond Tsirelson bound, essentially? Because we know that if we take these probabilities and adjust alpha beta in an appropriate way, then you can achieve certain violation of the Bell inequality, but up to so-called Tsirelson bounds. For the Clauser-Horne Shimoni-Holt inequality, these bounds are plus minus 2 square roots of 2. Here I am using Clauser-Horne inequality, which you can see here, for rotationally invariant probabilities. So that's how the classical inequality looks like. This is the quantum one. So you have maximal, Tsirelson bound, and minimal. Here you have absolute bounds, because these probabilities cannot be greater than 1/2 each because of rotational symmetry. Then such a number cannot be greater than 3/2 and cannot be smaller than minus 1/2. Yeah, because of this. Now the question is if we can find a model such that we will achieve these bounds, at least one of them, and the answer is yes, and it's very easy. Namely, you just take, instead of G1, which corresponded to these probabilities correspond to G1, which means first level of the hierarchy. That's why you have 1. If you had L here in the product, which means, or GL here, then you would obtain an expression like this, and you would have to estimate. Well, okay, the simplest way of doing this is to call it a single, just take these concrete parameters which were used for the maximal violation of the Bell inequality or Clauser-Horne inequality. Then you have a function which depends on 2 parameters, L and theta. G is just this function. This is G, yeah, the one which reproduces quantum probabilities. And then you just look what happens if you take another next levels of the hierarchy. So level 0 corresponds to the classical inequality. This is level 0. This is level 1 inequality in some sense. We will come in a moment to it. But notice what happens. I'm using addition and subtraction from level 0 here, whereas probabilities are from level L. Yeah? And if just take L0, then you have just no violation of the Bell-type inequality, which is this one. If you took GL and then minus L and plus L here, then you would not have violation of this inequality. It will be satisfied, of course, because it could be proved. Yeah? You are not able to prove it, therefore it can be violated. Yeah? So if you had L equal 1, then you get maximal quantum violation, which is a Tsirelson bound, and then you next compose it with itself several times, and you can very quickly achieve almost -1/2 very quickly. So it's a Cauchy sequence. And in technical terms, the proof is just like Banach fixed point theorem. Simply this one goes to 0, this one goes to 1/2 for theta in certain ranges. So this theta equal pi4 is not essential. It can be, yeah, okay. Yeah, that's nothing. So now the final slide with the bibliography. So this is the first paper, which was where I already announced that I'm able to do it. But here I discussed these projective bits, and I also discussed the relation between this projective product and tensor product, because I claim that this projective product of real numbers is something in between ordinary multiplication and tensor multiplication. Here, this is a paper which appeared in January, and this is the exact quantum probability for a singlet state, the construction. Here you have something where you can read a little bit about other aspects like dark energy and dark matter. Here I have a kind of review with certain aspects related to quantum mechanics as well, but also some elements related to generalized thermodynamics, because there are interesting thermodynamic aspects of it, because in generalized thermodynamics like Sally's thermodynamics or something like that, this kind of calculus is used. So this is another area of physics where people already started to use this kind of non-Newtonian calculus, although they were not aware that it's known, so to say. So the works by Kaniadakis on relativistic thermodynamics, they implicitly use non-Newtonian calculus, and I discuss these things here. And this is the newest preprint where I discuss in detail the Tsirelson bounds and stuff like that. Thank you very much.